Okay, LeetCode 226, Invert Binary Tree. This is also grind 75 number 6 for those of you who are keeping track. And in this problem, we're given a root to a binary tree. We want to invert that tree and return the root again. This is a pretty simple recursive problem, although there is an iterative solution to this as well that I will be going through. But first, let's draw out our thought process as always. So for the recursive solution and for the iterative one as well, the crux of the problem really is to figure out how to swap like the roots themselves. So I feel like that's kind of the hard part. And basically, let's say we're at this node, right? When we invert this tree, right, we want to kind of imagine a symmetry going down this tree right here. So if I have this big tree right here, that's like the symmetry of that big tree. But I also have baby trees, right? These little subtrees, and they themselves also have a symmetry. So I want to swap these nodes as well along this imaginary line of symmetry. Well, how do we do that? Well, that's pretty easy, as we'll see. And you can kind of already see why this is a recursive problem or a great candidate for a recursive solution, because like I said, you have this giant tree that you want to reflect along this. But then you also have little baby trees like this, right? And you want to do the same thing to them, and you keep going, going, and going. And if you want, you can even think of like individual nodes here and here as like baby trees too, kind of. So let's get into the code, because I think it's a lot easier to explain for most recursive solutions than actually drawing it out. So what we're going to do is, as with most recursive problems, you need a base case to know that to know when you should return from that recursive solution. So our base case is going to be if there's no root, then we're just going to return a null pointer, right? Because eventually, as we go down our tree, eventually we're going to be like here, right? And we'll see that left and right, so we don't have anything, right? And eventually, as you can tell, as we kind of hinted before, there's a symmetry, so we're going to be doing swapping. So that means accessing the children nodes. Eventually, we're going to access, like, let's say, the leftmost node of the child here, of one, the child of one, which is going to be this node, but it's going to be null. So we're just going to want to return a null pointer to say, hey, look, there's nothing there. That's pretty simple. The other thing we want to do is we simply want to swap the left node and the right node. But now that I write this out, I think I shouldn't be writing it like this. So in C++, you can just write swap, and this is a standard library thing. It'll do it for you. I think I'm not going to do that because I don't know if all languages have this. So instead what we'll do is we'll make a temp, or we'll make a tree node pointer called, let's say, temp right. And this will store the current root and its right child. So we'll do this. And then we'll say that root right should equal to root left, right? So we're setting the right child to the left child. But now that we set the right child to the left child, there's really no way to set the left child to the right child, right? Because the right's already pointing to left. So it'll just end up being left is pointing to left. And so that's why we're doing this temp right thing, right? We want to store it temporarily because we eventually want to do this. We want to say root left is equal to temp right. And that's how we do a swap. In fact, I'll just comment this in. I'll say perform a swap. Cool. So we have that. And then next what we want to do is we want to recurse. Like we talked about, there's tiny little baby trees, because if we go back in Paint, let's say we were at 4, right? And we want to swap, let's say we swapped 2 and 7, right? But 2 and 7, they are node pointers. That means when we swap them, when we swap their positions, we're actually doing this, right? Because since they have pointers themselves to their children, what we're doing when we're swapping 2 and 7 is we can think of it like this visually. Let's take this and put it here. Take this and put it here, right? So this goes here. This goes here, right? So we achieved this like symmetry along the big parent tree, right? Like, so 7 and 2 have been swapped, right? It's just like this picture right here on the right. 7 and 2 have been swapped, but their children haven't yet, right? They're not in the right places. They still need to be swapped. So we need to recurse further. And now let's say we're looking at 7 and we look at its children. So we say, okay, 6 and 9, you guys need to swap places, right? So we do that. Eventually we, let me just make this a little cleaner. Oh, why can't I do this today? There we go. We do this. And then we look at 2, right? Because obviously we're going to go back and we're going to look at 2. We're going to say, okay, well, your children need to swap too. So 1 goes here, 3 goes here, right? And it goes like this. And eventually, there you go. We look just like the picture on our right. So we need to use recursion for this. Sorry. So I'm going to say use recursion, if I can spell. And then what we want to do is we want to say, okay, well, root right, or let's do left first. Root left is going to equal to invert tree of root left. So we're going to recurse on ourselves. So we're going to say, okay, well, make the left child be like invert the left and all of its children, pretty much. That's what we're saying. So we do, and then we do the same for the right side. We do root right equals invert tree root right, right? That's all we have to do. Saying right too many times. Okay, and then at the end, we just want to return the root because we've modified it enough. So we do run code and misspelled. There we go, run code. Should work. Let's run the example test cases. They all work. We submit. There we go. It's pretty slow according to LeetCode, but let's try again maybe. There we go. It's getting faster. It's always random. So that was the recursive solution. As you can see, it's pretty easy and straightforward. Like when you read the code, you can kind of picture what's happening, right? If we don't have a root, if we reach the base case, we have nothing. So return null pointer. We end up swapping the left and right nodes. And then we end up going further into the child nodes and swapping those as well. And we do this over and over and over until it's done. So runtime, this is an O of N, a runtime solution. This is also an O of N space solution because there's an implicit stack due to the recursion. Okay, so there's that. The next solution that I think I'm going to do is I'm going to talk about the iterative solution. And the iterative solution is kind of annoying. It's not annoying. It just uses, it's longer. And we're going to use something called BFS, or breadth first search. And we're going to basically traverse the tree level by level. And we're going to swap the nodes that way. So what we're going to do is we're going to still have our base case. I don't know why I deleted it. So if there's no root, we just want to return null pointer. Otherwise, we're going to make a queue. It's going to be of tree node pointers. We'll call it queue. And we're going to push the root onto the queue. So we do queue.push root, right? And then while not queue.empty, so while the queue is empty, what we want to do is we're going to say tree node pointer current node is going to equal to queue.front. And then since in C++, when using queues, just accessing the front doesn't pop. Like in Python, you could do, I think, queue.pop, and they'll both give you the front, and it'll also pop it for you as well. You have to manually pop. So we do queue.pop. And then what we want to do is we want to say, okay, well, if current node, so, we want to say this. Yeah, if current node left, so if there's a left child, we want to push that. So we do queue.push current node left. We're going to push that onto the queue. Similarly, we want to say if current node right, we want to queue.push current node right. Cool. And then finally, we want to swap these two nodes. So we want to swap current node left and current node right. There we go. At the end of all this, we just want to return the root. And I think that's pretty much all there is to it. There you go. All the cases work. We submit. There we go. It runs. It's pretty slow for some reason. There we go. It's getting faster. Runtime. This is O of n. And this is also linear in space because instead of that implicit stack, we have that queue that we're pushing elements onto. So yeah, pretty straightforward, pretty easy. I hope you enjoyed, and I hope they helped you out. And yeah, thank you.